Okay. So let's get started. We are at which lecture? 6, right? No, 6, yeah. So this is lecture 6. And just to give a quick summary of the short last week. So last week, we took the transfer matrix approach a step further to look at the magnetization and correlation functions. And so we derived that the magnetization is given by the largest eigenvector acting on the spin configuration and the largest eigenvector versus the correlation function we found to be dominated by the ratio of the smallest and the largest eigenvalue, and correspondingly also the products of this largest and smallest eigenvectors acting on spins the distance r apart. And that's led us to also find that the correlation length is given by the logarithm of the largest, the smallest eigenvalue. We saw when evaluating that there's no phase transition for the one-dimensional Ising model, except for like the case of sending the temperature at exactly 0, which is not in any regards relevant. And so this discovery led us to the concept of the lower critical dimension. Which defines the minimal dimension at which fluctuations are sufficiently costly to not always destroy long-ranged order. And so the example is the 1D Ising model, where if I go in and I flip some spins, then I don't pay for how many spins I flip. I only pay in total an energy of 4J, which is only accounting for the two interfaces between the spins pointing up and pointing down. But at the same time, I have multiple positions of where I can put the spin flip. I could start here or there. So actually doing a spin flip gives me a sufficient gain in entropy, which is given by 2 kVt ln n. And so for a sufficiently large lattice, I always arrive at this being larger than the energy that I have to invest into the spin flip. And so fluctuations are not costly in energy enough to combat entropy, and we don't see any long-range order above 0 temperature. And that's already different if we go to 2D. So if I here flip, maybe the other color. So if I here flip 3 spins, the screen, yeah. Then I actually pay a cost that is proportional to the amount of spins that I flip, because here I pay at every boundary, and so In fact, the energy that I have to pay for the spin flip grows with the power law of the amount of spins that I flip. And so the energy becomes sufficiently costly. And we're going to see that for the two-dimensional Ising model, there are phase transitions. Not today, but maybe on Friday. Because today, we are quickly going to look into the generalization of the transfer matrix approach. And then we're going to do one more exact solution here of a 1D fluid model. So that you see some fluids as well. No, I'm joking. So there's a reason, like this is, it's quite fun that I'm allowed to teach this. So when I was a PhD student, my colleague and really longtime friend, he actually, in his PhD project, had to use the exact solution of the 1D fluid model. So it turns out that you, knowing these basic models may come in handy where you don't expect it. So what he was studying is actually, like when we take our DNA, right, it's super long. So to put it into a cell nucleus, we have to compact it. And so we do it with so-called nucleosomes. So these are like proteins that sort of wind up your DNA and thereby compact it. And so he studied like what's the positioning of the nucleosomes on the DNA and how does it affect the properties of the DNA and its functionality. And so this is actually like looking at the same physics as looking at gas particles positioning of nucleosomes in 1D. So you can look at this as also learning something about your DNA. And so another reason to look at the 1D fluid model is that here it's a nice example to combine both the continuum versus the lattice gas approach and see that these give equivalent results. Which I guess, for spins, you kind of believe me that, okay, sure, we're going to look at lattices. But for gases, it's kind of like, it may feel artificial. And so that's why I find it useful for you to show that these are equivalent. And if I'm super speedy, which, there's no need to, it's fine, like just interrupt me with questions as much as you want. But if we are, then we start with the series expansions. To then solve the 2D Ising model. Or like not solve, to solve, to learn about. It's not exactly, it's not the exact solution, to learn about. Okay, so that's the plan for today. So we start with a generalization of transfer. Oh, I should have mentioned this. Okay, so actually, like this nucleosome, he was a PhD student of Oli Galland, actually. So there's an action there. I'm not the only link. So Oli was a professor at the LMU where I did my PhD at the time. So Oli knows this quite well. Okay, so for the generalization, we here follow Carter chapter 6. Okay, so I had briefly mentioned already that the transfer matrix approach, what we do here is actually we have here all possible SI states in a matrix. And then here along this axis, we have all the Si+1 states. And this defines our transfer matrix to go from I to I+1. And so we can also, now what we're going to do is we're going to generalize to continuous variables. Which is, for example, the Heisenberg model, where now the spins are vectors with vector components along the Cartesian coordinates. I still, which just for illustration, looking at the simple case of no external field. So our Hamiltonian is going to look like that. Just, since I'm assuming you're using the, you may use that I give the books, and you may look into the books, you will realize that there are different notations of like spins are called sigma, I think, in Neumann's books, and S and Carter's book. Neumann's uses J over beta, J over beta, no J times, but whatever. So it has a J here, and Carter uses beta times J as K. So this is all the same. And I try to be consistent, but there's only so long. And actually it's gonna turn out that as we pursue, keep on going, that's going to be sufficiently costly to actually write beta J all the time. And so I will eventually swap to the K. Let me just stick in the notation of the reference right now. Okay, so now these are vectors, right? And so my partition function then looks like taking the trace of over all the SI, where now my summation is over SI plus 1, which I can also write as factors of K S1, S2, e to the power K, S2, S3, and so on. And so as before, we see that this should be the trace of a transform matrix to the power of A. Where now, since when you have continuous variables, we define the transfer function e to the K S1, S2 as S1 acting and as before, we would like to bring the transfer function into diagonal form. And so we do that by writing it as a function of its eigenvalues, the alpha and the eigenvectors, such that is then this one alpha S2. And so now we can identify that these are functionals because we have continuous variables. And we actually saw these kind of functionals before in a different class. But this is basically us being able to do certain operations in a certain limited of space of math that is nicely solvable. So that's the connection, not that we're looking at a quantum mechanical feature, but basically here from the plane waves in quantum mechanics, we know that the exponential a dot product can be decomposed in terms of the spherical harmonics Y, L, M. And so by this mapping, we can see that now this functional becomes the sum over the eigenvalues are now enumerated by summing over L from 0 to infinity and M from minus L to L, right? These are the eigenvalues of the spherical harmonics. The enumeration of the spherical harmonics, minus L to L. These are the eigenvalues, I to the L, J, L. And then this is are the eigenvectors evaluated at the values of the spins. And here the eigenvalues note are independent of M. So we can see that in this case, the partition function becomes the trace of the exponential of the transfer function, which here now is again the sum over the eigenvalues in this case of the spherical harmonics, which as I said, they are independent of M, so we can evaluate the sum over the M's to find there are 2 L plus 1 M's times lambda L. Oops. This M is gone. Again, here the largest eigenvalue dominates at n large, so we only care about the largest eigenvalue. And so in this case, for spherical harmonics, we can actually this is short sine k over k. So this is just to show you that this approach of the transfer matrix is not limited to spins that have a finite number of degrees of freedom, but can be expanded into for continuous variables, and thereby you can just quickly map it to a quantum mechanical problem, which we solved already. The key essence that you have is like, yes, we can do this. Like it's limited to finite degrees of freedom. And the other lesson is that it's very cool if I can map it to a system, because the only thing that I still care about is the largest eigenvalue. And so if I can determine if I can write down my transfer matrix to the extent that I can estimate the largest eigenvalues or the scaling of the largest eigenvalue, I'm actually in charge of learning a lot about my system. Yeah.
I don't know if it's a stupid question, but the lambda sub Lm is the eigenvalue, right?
Yeah.
Okay, and what happens with the spherical harmonics?
Oh, they're normalized, right?
Oh.
So if I I'm I'm taking the product of all of them, and then since they're orthonormal, I just get a one. If I keep going from, this is the one for K as 1 as 2, and then I have complex conjugate. If I then take e to the K as 2 as 3, then I have the complex conjugate of this one. And so since they're orthonormal, these will all be ones. And if I haven't specified that, but we were still using periodic boundary conditions, right? So I'm going from Sn to S1. So I'm actually taking the loops, and so they all come out as one. And that's why we go to the eigenspace, right? Because we know this property of the eigenvectors, that they should be orthonormal onto each other. And so we know that it's only governed by the eigenvalue dynamics. And that's why we do this. We always want to go express the transfer matrix in its eigen decomposition. Because then that's the only thing that we can only care about the largest eigenvalue. Otherwise, we would need to go nitty-gritty and actually evaluate all these sums if we don't go to this eigenspace, which makes the calculation simple. Yeah.
Okay.
Cool.
Thank you.
Yes.
Why n to the power of, what is it?
This one?
No.
No.
A little bit on the right.
Yeah. Right. Oh, that's a conjugate star.
Oh, okay. Yeah.
That's me trying to do a conjugate star. Let me try again. Like that? Yeah. Okay. More notation. Sorry. Yes.
What happened to the last equality that okay, you summed. Okay, yeah. I mean,
No. Like this is I'm just like, this is like Wrigley's. So this is just saying that in the end, in the sum, if I normalize again, that it's only the largest eigenvalue that will govern, right? So I have a sum over eigenvalues, and I can write it as so I can write this as the largest eigenvalue. So there's still sorry, this is missing.
okay.
But it's the same, and then I have whatever, it's 1 and so on. And so what I can do again, I can write this as lambda 1 plus lambda.
Yeah.
Oops, sorry. Here.
And this the largest eigenvalue. What L does it have?
0 in this case.
Okay.
For spherical harmonics, it's the 0, 1 that's the highest, the largest.
Okay.
And so because then all these again go to 0 for n to infinity, because of this being to the power of n, right? Sorry, no, it's sorry, it's the it's the sum, because we're taking the trace first and then to the power of n. It's here are the power of n's coming in. Sorry, it's quickly correct. So otherwise it doesn't work out to the n, and then here it's n, and then n, and then they go to 0. And that's why it's only governed again by this lambda 0 to the power of n.
But the 2L plus 1 shouldn't be to the power of n, right? I mean, otherwise this argument, the 2L plus 1 shouldn't be to the power of n.
You're right, yes. But evaluated at L equals 0, it gives a 1. So that's why it doesn't come up. Yeah. Okay, more questions, because then we're going to leave the transfer matrix. Yeah. Okay. So then we turn to fluid models quickly and look at exact solutions of fluid model in 1D. And here we use Schwaduri and Stauffer, chapter 8.7. Okay. So how, since we've looked at spins for quite a while, let us remind us how we define a gas. And so, because I already advertised that we're going to look at it in a continuum and in a lattice gas approach, I will start with the continuum approach. Okay, so say we have particles in our gas, and now it's not an ideal gas because you solved that to various extents about a year ago, I suppose. Now we look at a gas that is interacting with an interaction term U of X I Xj. So these are individual particle positions. And then the Hamiltonian which is defined by the particle positions, and their momentum is then summing over their momentum, it's the kinetic energy, and then the interaction term, which where we're summing over the interaction of all particles with each other. And the summation runs for I smaller than j, so that we don't double enumerate, right? So that I'm only counting each interaction once. So one interacts with two, but two doesn't, I don't sum again when two interacts with one. And so because of this interaction term, I cannot go into the factorization of the partition sum, right? So because here again, if I go to e to the power beta of the momenta, and I want to sum over all the momenta, I have a sum in the exponential, and I can factorize the exponentials into products of different exponentials. But now we have this stupid term where particles are interacting with each other, and so we can't do this anymore. So what we have is actually we have to deal with the so-called many-body partition function. That where I'm enumerating over given that I have indistinguishable particles, and I'm summing over all degrees of freedom in the position of the particles and their momenta. And so one approach is to say, okay, here I have two terms, one that I'm very familiar with from the ideal gas, so, and one that I have no idea how to deal with. So what I can do is I can factorize the partition function of the ideal gas and only look at what is the impact of the interaction as a correction term. And so the ideal gas partition function is now the volume of space, and it's now better I squared 2m over and this is from evaluating these volume integrals. And so then I can write my partition function as product of the partition function of the ideal gas. This prefactor is left out, and then what I have left is e to the beta I small j. Which I define as the correction term Q, and actually reminding us of the evaluation of the ideal gas partition function. This is then 1 over faculty V over and Q. And so right now we only did massage, right? We didn't actually compute anything. So now the question is, in which setting can I actually evaluate this correction term and say something useful about the properties of the gas? And so, as for the spin systems, we are aware of our analytical limitations and restrict ourselves to 1D. And so 1D has one key importance, which is that if I have more particles and I put them in this in one dimension, I know they are ordered, right? So even if they're wiggling around in 1D, they can't move past each other, right? Because they're confined to 1D. And so this property makes it particularly easy to calculate the partition sum, but it obviously also shows that this is a very lucky coincidence of being 1D, because in any higher dimension, obviously the particles can swap ordering, and so the calculation becomes much more complicated. So just to go step by step, so in 1D, our Q is then b to the power of n, and then I would sum over the position of all individual particles, now enumerating them, and I assume that these particles sort of are positioned in 1D along a box of length L. So in principle, I have to sum over all these positions, e to the beta j u. And because they can't move past each other, the interaction can only depend on their distance, right? So now it's actually xi minus xj, because they're in space. And so we do one more restriction, which is we also restrict ourselves to nearest neighbors interaction. So that means that our interaction U actually then becomes a sum over all particles starting with 1 and going to n minus 1, because I only basically count the distances, right? between two particles. So now this is just depending on the distance of subsequent particles. Of particles. Okay, and also this note of warning that this is a very happy coincidence because no similar ordering is possible in higher dimensions. Okay. And so now to evaluate really a particular partition function, we now have to really specify this function here, this interaction, which now depends on the distance between subsequent particles. And so to do that, we'll look into the example of the so-called Tonks gas. It's again a name. And so the Tonks gas is kind of the simplest gas that we can consider because we only have of like the simplest gas of interacting particles, because obviously the simplest gas is the ideal gas, but of interacting particles because we only consider hardcore interactions. So that two particles can't be in the same spot because they have a finite size. So we have hardcore repulsion. So I define this U of x as infinite if the distance, and this is how I should write it, right? Is smaller than a infinite, oops, or 0 for bigger than a. Sorry, here my x. And so then our correction factor here becomes the following enumeration. So here we have a prefactor coming in because we said we're going to order our particles. But in principle, there's different, like, you know, I can take a red ball and a blue ball and have two ways of how I could order them on a lattice. So if I have n particles on a lattice, I have n faculty permutations. So this is just making sure that we keep the number of permutations on particles. And then we write down these integrals, which basically means that if I have my particle x1, and let me actually draw like that. So these particles, they have a size A, right? Each. So the position of x1, x2, x3, and here is 0. So the position of x1 can go from 0 to x2 minus a, right? Because there's a halves here and a halves here, where they can't get closer because otherwise they would overlap. So that's why it's the hardcore potential is the easiest, because I don't actually have to evaluate this exponential of the of the interaction, but I just have it act by choosing the integration limits appropriately. So x1 can go from 0 to x2, but they always become alphas, x2 minus a, and then similarly dx2 can go, so the furthest it can be to the left is if I move all my gas particles completely to the left, right? So if I could move them completely to the left, then x1 is going to be at a over 2, and it's going to extend until a. Until a. So how do I position? Oh, sorry. Let me quickly. So the positioning of the particles is enumerated that way. Otherwise, just said didn't make sense. So x1 starts at 0. Oops. Starts at 0 and goes until x2 minus a, the size of the particle, and then x2, the furthest to the left it could start, it's just the distance a from the origin, and it can go until x3 minus a. So we start with a, x3 minus a, and so on, right? And then the x3, now we got it, we go and start with 2a, you go x4 minus a, and so on until dxn minus 1, where we have n minus 2 times a, and this is x n minus a, and then the case dxn, that's the other limit, because this is the size of our box L, so it can go to L, and is here limit by n minus 1 over a. Yes, Manuel.
So the gaps in the drawing are only in the drawing and not in the real system.
No, they are, right?
Yeah.
So I have like 3 particles, and they have a space of, say, 3 particles of size 1, and they have a space of 5. And so I'm just trying to figure out, like, how can they be ordered? Because they're gas, like they can move in the space, and so they can all, like, in principle, all like accumulate to the left, and all the rest is space, or they can equally put a partition. And I'm just summing over all the possible positions that the gas could have. Like I'm summing over all the potential states, right, of the particles.
And the very first particle, which can go from 0 to x2 minus a, where would x2 minus a be in this drawing?
I don't in x2 sorry. So in this drawing, this is x2, right? And so I chose to enumerate the position of particle 1 at its left end. So the left end can only be a away from a right boundary. And so now the position of the next particle, position x2, is kind of the left boundary, the right boundary, sorry, it's the right boundary of this particle. But since I'm enumerating its position by its left side, it's x2 minus a.
Yeah. Okay. I mean between the areas that you the ausgemalten Flächen.
Yeah. So this is the extent of the particle.
Und zwischen den ausgemalten Flächen ist im richtigen System keine Lücke.
Doch.
Oder doch, okay. Okay, then I have to.
So it's like you have maybe let's start with 3D system. So you have a 3D volume, and I put in like a few number of particles, and I want to count the configurations of these particles, and they are moving in empty space, and they have lots of places where they can be, right? They could be all accumulating in a tiny box in the far right corner of my big box, but most likely they have lots of regions where they could be. And now what I'm doing is I'm saying, like, oh, actually these particles can't be everywhere, which is what I can assume for an ideal gas, because they are point particles, but they actually have to be at least a apart from the next neighbor, because they have a finite volume of a in 1D now, right? And so what I have is that I have these particles, and they if this is my space, okay, and I need to enumerate which potential positions can they have. Obviously, it depends on the size of the box. We should have that come up, right? That this plays a role because the size of the box, if the size of the box is exactly n times a, there's only one configuration, right? That means that all particles are lumped exactly together. But as soon as L is bigger times n times a, I have different potential states available. And I would sum over all of them. And so the way I sum about them is to sum over the positions of each particle. Given that I now, having in mind this very simple interaction of a hard potential, I can really enumerate their positioning.
Okay. Yeah. No, it comes to
Yeah, it's like all of a sudden we jump from spins to fluids, right? To fluids to gases. Yes.
Do you mean L minus A in the last boundary, or do you want?
It should L minus A. You're right.
And another thing I'm wondering about is the n factorial. Is it to cancel the n factorial above from the partition sum, because we can in fact distinguish between particles, or why do we have this here?
Yeah, because the particles are now ordered, and so we can distinguish between them. Yeah. Yeah. Yeah.
The factor volume to the power of n to normalize.
Yeah. I know this is
like
no, it's n in number of particles, and they all have a v volume, which so it comes from here, right? That this exactly. So the volume, no, not L. V is the yeah, L to the power of n, right? In this case, it's L. Yeah, should be. Yes. But I'm just going to keep it this V of n, because in the end, what I'm going to do is that we are interested in the partition function. And so this V of n will cancel with this V of n again. So if I just change variables now, but yes, the meaning is L, because we're in 1D, because we went from here, this being the full formula, to making all these assumptions. But in the end, we're going to calculate this correction term. I'm just going to drag this along, and then we know it's going to cancel again. Okay. And now to evaluate all these integrals, I'm going to do a trick, which is now we make a change of variables of defining y as xi, minus I minus 1 times a for, I don't know where for I equal 1, 2, and so on. And so then, no, there's no integration factor coming up. I'm just copying down this one, dragging it along. And so then instead of integrating over x from 0, x1 equals 0 at I equal 1, that's again 0, dy1. But now the upper limit becomes so we did the idea, I set this up directly so that this a cancels out, right? Because now I have here x2. This is actually, so if I evaluate this at I equal 2, right? At I equal 2, I have x2 minus a. So x2 minus a, this is exactly y2. So I'm integrating from 0 to y2, and I get rid of these integration limits having these minus a's. This is basically the trick. And also that the lower limit now, I also get rid of the a because that's also subsummed in here. So I'll start at 0 and go to the next higher up. dy3 to y4. Now we got it. 0 dy n minus 1 until yn, and I only have to pay attention here because now this goes. Let's see if I get rid of the I n yn. So anyway, let me just write it down and then we get this together. So I go to because now my yn, so this is I changed the variable, so I have this n minus 1 factor in here, the a, and it's consistent to the extent that I previously had my integral going up to L minus A, and then this would follow L to L, and now I have this L n minus 1, and it should be Ln minus 2, but this would bound propagate to
Isn't it L minus NA?
no, because yn, I have n minus 1 here. So it would be n minus a. N minus 1 a. That's consistent with this. But
I insert for xn in this equation L minus a in the upper limit.
yes,
So
I know. So that's what I'm staring at. So right now, what I'm upset about is that we added this one, and this is not propagating through. That's why I'm staring at this. The minus a is missing. Here, it would be an additional minus a.
Yeah.
Yeah, and I cannot explain why, but the results would change if I have it there.
Oh.
So this is me staring at my notes and like being upset about this.
Well, I mean, you can always change the volume to L plus a, right?
Yeah, I think that's what we have to do. We have to change it from L plus a to L plus a. Because it's the like where can it be positioned on the right? And then I think that's let me just do this. This is what I was so just changing the drawing, which is L plus a. Yeah, okay. Not super happy. No, anyway. But okay, so the cool thing that now that we changed our integration limits is that these integrals we can now evaluate if we evaluate them bit by bit. So now integrating over y1 and reordering integrals. Just back dragging these along. So now if we integrate y1, we get y1 that we evaluate at y2 and 0, so we get a y2. And so the reordering I do because we need this y2 when we then integrate over dy2, right? So let me just move these forward. So the n0 0 n y3, and then we have this y2 from the first integral that we evaluated. And now we can go on, right? So now integrating over, over y2, we got we get a half y3 squared, right? And if we also integrate over y3, we actually really see the pattern that comes up, which is that we have factorials for the number of integrals that we need to evaluate. 3 faculty y4 to the power of 3. And so in total, what this results in is that Q is n faculty Vn. So we have at the end we go until the upper limit is L minus n minus a1a. So that's how you see how I really bothered about this upper limit, because this is what comes down here. Ln minus 1 over a to the power of n. And we normalize with this factorial coming. And so now we have a really neat closed expression that I'm going to take, and now we're going to cancel this v of n again, because I'm going to plug it into this expression here again. And now you also see how these permutations actually cancel out again, so that we're left with the partition function. Set the n factor. That's all. Yeah. And then here we have the L minus n minus 1a. Sorry, there's an n faculty missing here. Of n. And so from the partition function, we get the free energy per particle. I decided to call this a small f. And to take this, to define this, we take the limit of n to infinity, but at the same time keeping also L to infinity, but keeping the density, if you want to say so, which I call small f, fixed, right? Of minus kbt and then z, that's just a definition, and it results in minus kbt of minus ln plus ln. Now we have L over n minus a plus 1. And this is what I define with my density. Okay, so this doesn't yet look maybe like something that you recognize, but just give me one more line and you're like, oh, I've seen this before. So then the equation of state for the Tonks gas is now taking the derivative of this free energy with respect to the density at constant temperature. And so doing that, we find kBT 1 over v minus a. And so where have you seen a similar term, at least? Not exactly that one.
No.
Yeah, the extruded volume, right? So everything's consistent, which is good. Anyway, yeah, this is our extruded volume. So if we just rearrange into our comfortable form, we see that the volume is reduced by the excluded volume and the density. And density in this case. I think this is actually what we, let me quickly just rearrange it because we're used to or rearrange as P is KBT over V minus A. So here we can see that as our individual volume approaches A, like if we make the volume available for every particle close to A, the pressure diverges, which is what our intuition would also tell us as V over A. That would be at close packing. Okay, but now, I mean, we're in advanced statistical physics too, and so we're interested in like phase transition. So can we see a phase transition? So again, what are we hunting for? We're looking at discontinuities or divergences of the response functions. So let's have a look at the response function. So, for example, the isothermal compressibility, which is defined as 1 over B dV dP. And this is why I also rearranged this as a function of V, because now we can take the derivative with respect to P. So let me just quickly down. So this would be dP of KBT over P plus A, and that's minus KBT P squared. And let me rearrange this briefly by plugging in again the value of P here. So then I have it's because it's P squared, one of the KBTs cancels, and I can write this as, and I cancel the two minus signs. So I have 1 over V, V minus A squared over KBT. So why is this a useful description? Because now I can look at, what's the size, or like, does it change sign, right? Is there something interesting happening? Turns out no. So we know that the volume always has to be bigger than A, right? So this is always, and it's squared, it doesn't matter. Like whatever we do, like if this is a positive number, the temperature is positive, like everything's positive. So there's no phase transition, which we could have directly read off the equation of state. So because if we plot that, the pressure versus V, I know that the pressure diverges as V approaches A, but otherwise it's like a happy decay. So there's no coexistence of gas and fluid phase. Boring again. But you can describe the positioning of your nucleosomes on your DNA, right? So we learned something anyway. So no coexistence of gas and liquid phases. Also, we get this from the isothermal compressibility. Because it's stable at all times. Okay. And I told you, okay, we don't find a phase transition as we did in the 1D Ising model, which is why we're going to go to the series expansion later on today or this week. Actually looking at this gas is very cool as well, because I can show you that really a lattice gas description gives the same results. And so it's you are free to make the choice if you want to describe gases, if you prefer to do the calculations continuous phase or on a lattice. And so to drive that home, we're going to look at the Tonks gas in a lattice gas approach. And so now the approach for a lattice, and that's the advantage of lattices, is because now you have finite number of states, because now we have a lattice and it has n sides, like n, there are nl lattice sides, and I will position np particles on them. And so now it's just enumerating, and you can go back to if you did your high school degree in Bavaria, I trust that you had lots of statistical physics. So this is now going back to all these populations and just enumerating and calculating the entropy. So depending on how much you like this might be your preferred choice to calculate the Tonks gas. And if it isn't, then you saw the other one, and maybe you're going to learn something by just looking at the statistics. So as Tonks gas only has a hardcore repulsion, we can calculate the entropic contribution to the free energy using combinatorics. And lattice, and then take the continuum limit. Okay, so just a few definitions. Okay, so we need NL. These are our number of lattice sides. And then we have LP, which is the number of particles. And we consider a lattice. So the lattice also has the lattice constant, which is now A0, which is the lattice constant. So we know that the length of the lattice is NL times A naught. And now we consider a hardcore repulsion as a function of phi of r, right? Distance between particles that is infinite if r is smaller than this. N is now enumerating like how many lattice sides I need to place this volume of my my gas particles, or it's 0 if I'm further away. Small n, lots of n's, sorry. And so what we can learn is that we actually have NL minus n, and lattice sides do we need for each particles, small n, times the number of particles lattice spacings are available. So empty lattice sides. So this is the volume measured in so lattice spacings are available to distribute NP plus 1 gaps in between NP particles. So again, if we go back to our image, so why do we have NP plus 1 gaps? We have NP particles. Well, because you have a gap between 0 and the first particle, and you have a gap between the end and the last particle. And so in between you have NP minus 1s, in between the particles, 1 to the left, 1 to the right is NP plus 1. So these are the gaps that we can distribute on the space that is available, namely NL minus NP. And so now the number of ways to distribute these NL minus NP identical rods, each of length A0 among NP plus 1 identical boxes is the correct definition. So number of ways to distribute N minus N NP rods So that's then NL minus N minus 1 NP faculty over NL minus N NP faculty. And so from that, different combinations, we enumerate the potential space, and so we can directly calculate the entropy, which is then given by KB ln of this function again, NL minus. Okay, and so since the entropy is defined as the first order derivative of the free energy, we get in this case we have S is minus the F dt constant volume, so we can integrate the entropy over time at time temperature to get the free energy. Sorry for that. So that's then KBT ln NL minus N minus 1. And so this and then if we have the free energy, we can go back to our equation of state, right? Because that's, as we did before, we want to have the pressure. So then P is minus dFdL. Where L is actually NL A0, right? We defined that here. L is the volume, right? The 1D volume. And that's then minus KBT 1 over A0 D NL. Ln okay, And so that's a clumsy derivative. So the way out that we have used before when calculating entropies this way is to take the limit of n large and using the Stirling formula. Which says that ln of n faculty, is n ln n minus n plus terms of order ln n. And so then I just divide by kbt, we get 1 over a naught. And again, we take then the limit L to infinity, and P to infinity, but sorry, keeping the density constant, N over L, N, wait, sorry, density, volume over NP, I define as small v, our density again. And so if we use this, if you use these to simplify these factorials and then take their derivative, we arrive at an ln 1 plus np a naught and L a naught minus n np a naught. And now taking this limit, we arrive at ln you can already recognize a few features that we had discovered in the continuum model, right? Because this term, for example, you have v minus na, and na was just the size of your particle in units of lattice constants, right? So this is actually our a, and so now taking the continuum limit, we take the limit of a naught to 0 and n a naught, didn't write, n a naught goes to a. Oh, sorry, I had lost the prefactor here. A naught and 1 plus. Then becomes and a naught capital, so we're back to the same equation. So it's the identical to equation of state obtained via continuum approach. So we learned that taking continuum limit in the correct manner, like we did here, then a lattice gas is equal to a continuum gas. Yet very boring because no phase separation. To condensation, no liquid phase, and and so, okay, so you can say that, why didn't we have condensation? Well, because condensation, we would expect that there has to be an attractive interaction, right, between particles, because that's what's driving them to condense. And here we obviously didn't even include that. We just looked at hardcore repulsion. So no wonder. One could go a step further and actually include short-range attractive interactions in this 1D gas. That's then called the Takashi gas. But even there, if the attraction is short-range, it won't be sufficient to drive phase separation to condensation in 1 dimensions. So again, underlining that we'd really be interested to have tools to not solve just 1-dimensional models, but actually learn about 2-dimensional systems. So also with interaction in 1D, which is Takashi gas. Oops. We have no condensation. No phase separation. But, as I said, whole application, the ordering of nucleosomes on your DNA. And if you want to know details, you can just go one flap and talk to Ulrich Gallant. He knows more. Okay, so this nicely underlines, and I'm like, yeah, okay, I can start a little bit. This nicely underlines why we would like to have capabilities of 2D. Go ahead.
In free energy above, why is there no minus sign? Because if you integrate the entropy, or
oh, did I miss it?
The free energy.
Yeah, I think we just and then I dropped it, right? The minus sign. Okay, wait, let me just so there's a minus sign, and then it's gone here, and then it's consistent going down, right? And then yeah. Yeah, sorry. Okay, so 2D, right? All the interesting stuff starts happening in 2 dimensions. What can we do? And so the next topic is to look into series expansions. And the idea is to expand from look at the partition function and try to expand it in orders depending on if you start with a high temperature solution and also start from the low temperature solution and sort of expand in orders of like decreasing or increasing the temperature, and thereby see if there is critical behavior, because if we start from these 2 limits and we see that they all, we can see that there should be a divergence happening. So we can learn about phase separations of the system without actually solving it explicitly, which in fact for the 2-dimensional Ising model you may, but I decided to spare you from all this whole lot of math, which I'm not sure that you gain physical understanding of the process, but the series expansion is like a universal tool that was developed just before the randomization group approach, and really gave insights already about not only critical phenomena, but also universalities of behavior already. But just then randomization group actually became it as the most powerful tool and then did it all. But it's very instructive to learn about this method as well, because it might be more suitable in whatever you're dealing with, rather than sort of you can always assess like which tools are easiest, And maybe what you learn about this with this tool about your system is already sufficient. So the idea is to start with series expansion. And here I recommend Yeomans chapter 6 and Carter chapter 7. And so the idea is we look at lattice models. And the idea is to start with an exactly solvable limit. And represent perturbations around around such limits by graphs on lattices and hope that with successive approximations, so taking into account higher orders, which means in this case more and more graphs enumerating on lattices, that we gain information about critical behavior yet the challenge is with higher order contributions, they rapidly explode, basically. The number and complexity increases rapidly. So there's a rule of thumb that's like say you had it to the 5th order, then enumerating all the potential perturbations that you have to take into account for the 6th order is equal to the amount of work that you had to put in for all other orders up to 5. And so for 7, then it's equal to all the effort you had for 6, and so it's increasing rapidly. So equal to the effort of all previous terms. But it's, in a way, it's kind of neat because I mean, it's not neat that this goes up so rapidly, no, don't get me wrong. But what I like about this approach is that you solve like you enumerate your analytical terms by really visualizing them on graphs. And so there's a high visual combinatorics component that, as I said, like depending on how much you got frustrated by combinatorics at high school, that might bias you to that view, but whatever. Let's have a look at that anyway. When we're going to start the high temperature series expansion on Friday, I suppose. So that's the first thing. We're going to start with the high temperature series expansion, and then we follow with the low temperature series expansion. They and they offer different insight, but actually can tell you a lot about the system. They will follow a few, for quite a few number of lectures. Okay, so with that, I'll quickly stop the recording and I'll